In this video, I'll be explaining to you two different things. One problem is a regression problem, and the other one is a classification problem. So this is a plot for the regression problem. I have my x and my y, so I try to visualize them to see their relationship. So because of the nature of this relationship, I suggest the polynomial function space. So, but I have to also define my loss function. Yes, the L2 loss is suggested here. And after that, I have to also see which polynomial or which degree of polynomial is best or is the optimal for this problem. And no, this is a regression, as I said earlier, it's a regression problem because the function takes s, which is a continuous variable, and spits out y, which is also a continuous variable. So it's a regression a problem in that case. So I just built the error from with polynomials degree 1 to degree 10, and I'm trying to do the cross validation to see which one has the minimal error to pick as my optimum optimal degree of polynomial. So in this case, the degree of polynomial 10 has the smallest error. Okay, so this is a plot of the cross-validation error with that of the empirical risk on the polynomial degrees. And as the plot suggests, you see that polynomial of degree 10 has the smallest error in both cases. And I'm also trying to compare the models, the optimal model, the overly complex, and the simplest. The simplest is just a black line, the straight line, which is a simple linear regression model. And also the optimal is the one with polynomial of degree 10, and the overly complex, I use polynomial of degree 16. And as you can see, the optimal and the overly complex are both, seeking to do almost the same thing, but the optimal polynomial or the optimal curve try to fit the data well with less variance as compared to the overly complex one. So doing the box plot to check which of the models will be better, and the choice lies between the complex and the optimal. And in this case, I'll go for the optimal because it's evident from the curve and the errors printed. Also, the ANOVA was run to check which of the whether there is a statistical difference between the three models. And as you can see from the p-value, it is evident that at least one pair of the models is statistically what different. And this is the confidence band and the prediction band to show how our data is predicted with our, how we predict new values using our model. And the confidence band describes the uncertainty around the mean estimate, while the prediction band account for both uncertainty of the mean and variability of individual observations. So the second problem is a classification problem where we use the spam data to try to group a certain email into a spam or not a spam. And this is the distribution of the response variable, which is type of email. And as you can see, the non-spam is more than the spam in the response variable. So in that, we'll try to build some four machines, which is the LDA, QDA, the naive Bayes, and the FLD, to see which of these machines best classify these messages into spam and non-spam. And as you can see from the ROC, the AUC and the ROC curve, can see that the LDA and the FLD are almost doing the same thing with area under the curve as 0.961, which defines their performance. Okay, so we choose between one of them, and these are the errors from each of them, each of the four models. So this box plot also try to define which of them will be best for classification, and the choice is between FDA, F, F, L, LDA, and FLD. Okay, and then from the box plot, you can see clearly that there is no difference much between LDA and FLD, and QDA seeks to have the highest variance. So we can pick the LDA or the FLD, or we can join the two to build a strong model to classify these emails. Thank you very much.